Welcome to the Explainer. If you follow astrophysics, or even if you just occasionally check the space weather forecast, you already know our sun doesn't just sit there quietly. It's actually operating on this massive, highly variable 11-year cycle. Sometimes it dips into these extremely quiet periods, like the famous Maunder minimum, and other times, well, it ramps right up to grand maximums, unleashing space weather that can directly mess with our satellites, our power grids, basically our entire modern way of life. But predicting exactly how strong the next cycle is going to be, man, that has been a notoriously massive headache in solar physics. But today, we are unpacking some truly brilliant new research that finally hands us a mathematical magnifying glass to solve this whole thing.
Okay, let's dive right into this. Here's our roadmap. We're going to cover the solar cycle mystery, the prediction problem, a groundbreaking new mathematical framework, testing the dynamo models, and finally, the secret to predictability.
Starting off with Part 1, the solar cycle mystery, a cosmic guessing game.
To really understand the future of our sun, we have to understand its internal engine. So let's ground ourselves in what we're actually trying to pull off here. When scientists talk about solar cycle predictability, what they mean is the ability to accurately forecast the amplitude, so the maximum strength, of that next 11-year cycle. And to do this, they use these massive computer simulations called dynamo models, feeding them data scooped right up from the magnetic fields we can observe on the sun's surface right now. Sounds straightforward, right? Well, here's where things get incredibly tricky.
Moving to Part 2, the prediction problem, reading the solar dashboard. The absolute core issue solar physicists are up against comes down to one simple question. How do you predict the mood of an entire star from just its surface? See, the magnetic field that actually drives the solar cycle is generated by this dynamo process, churning away deep, deep within the sun's interior, way down in the convection zone. But our telescopes, they can only measure the large-scale magnetic fields sitting way up top on the surface, specifically the polar magnetic fields during a solar minimum. Think about this surface field like the dashboard of your car, and that internal dynamo is the engine itself. We desperately need to know if the readings on that dashboard are actually giving us a reliable, honest picture of what the engine is about to do.
Which brings us to Part 3, a new mathematical framework, the detective's magnifying glass.
A completely brilliant 2026 paper by researchers Li, Zhang, and Luo gives us the exact tool we need to finally test that dashboard. What they did was take the mean field magnetic induction equation and mathematically applied Stokes' theorem to it. Now don't worry, you absolutely do not need a PhD in advanced mathematics to appreciate why this is so cool. Basically, this calculates the total fuel being generated for the next solar cycle. Just imagine a mathematical loop elegantly tracing from the solar surface, cutting across to the equator, plunging deep down to the base of the convection zone, and coming right back up the axis of rotation.
By creating this framework, the researchers managed to break down all that highly complex internal physics into 3 measurable competing forces. It's literally like a massive cosmic tug-of-war. Step 1 is I1, the surface induction integral. This is the data we can actually see. It's our visible dashboard. Step 2 is I2, representing magnetic flux crossing the equator. And step 3 is I3, which represents all the messy internal turbulence and magnetic diffusion happening deep inside. These 3 forces are constantly battling it out to determine the strength of the next solar cycle. And this leads us to the absolute golden rule of this new framework. I1 is the hero of our story here. For any dynamo model to be a reliable predictor of space weather, that surface induction integral, I1, has to completely overpower I2 and I3 in determining the net flux. If I1 is winning that tug-of-war, it means our dashboard reading is perfectly mathematically synced with the engine and the model has genuine predictive skill.
All right, Part 4, testing the dynamo models, interrogating the suspects. So the researchers didn't just stop at the math. They actually ran this framework through 5 different leading solar models to see which ones could survive the test. Let's look at a major success story. Model 1, a flux transport model. When you look at the data for this one, the total net flux generation rate, the actual engine, and I1, our surface dashboard reading, are practically hugging each other. They are moving in perfect lockstep, totally phase coherent. Meanwhile, the internal turbulence and equatorial crossing forces, completely flat. This proves definitively that in this specific model, the surface polar field is a fantastic, reliable predictor of the next cycle.
But contrast that with a spectacular failure. Model 3. This is a classical alpha-omega model operating without meridional circulation. In this scenario, the surface data totally loses the plot.
it completely loses phase coherence with the actual net flux. It's peaking at entirely the wrong times. And instead, those internal forces, I2 and I3, completely surge and take over the dominant role in driving the dynamo.
Comparing these two side by side really drives the point home, doesn't it? In Model 1, our hero I1 dominates, so we have a predictive model. We can trust it. But in Model 3, I2 and I3 take over. Going back to our car analogy, in Model 3, the wires between the engine and the dashboard have literally been snipped with a pair of cosmic shears. The surface magnetic field has become totally, spatially decoupled from the deep radial shear layer where the actual fuel is being made. You could stare at the polar surface fields of Model 3 all day long, and you'd be totally blind to what the next solar cycle is actually going to do.
Finally, Part 5, the secret to predictability, solving the cosmic mystery. So what actually keeps those wires connected? What separates the successful predictors from the spectacular failures? Well, out of the 5 models tested in the paper, an amazing 4 out of the 5 possessed genuine predictive skill, meaning I1 was dominating. We already saw Model 1 succeed and Model 3 fail. But here is the real kicker. Model 5 is highly predictable even though it has 0 meridional circulation. Why is that wild? Because for decades, scientists swore up and down that a strong subsurface conveyor belt was absolutely 100% required for predictability. Model 5 mathematically proves that is just flat out false.
So the absolutely crucial takeaway here is that there isn't just one way to predict a solar cycle. There are actually 2 totally distinct physical mechanisms at play. The first is flux transport feedback. That's where meridional circulation physically drags the surface field back down into the dynamo loop. That's your physical conveyor belt. But the second, newly confirmed mechanism is direct reflection. In this scenario, just like we saw in Model 5, the surface magnetic field inherently mirrors the interior dynamo simply because the dynamo operates throughout the convection zone. The surface isn't being pulled down, it just naturally reflects the processes happening immediately beneath it. Either way, as long as one of these 2 mechanisms is functioning, our dashboard works.
And this brings us to a massive, massive paradigm shift in solar physics. As a researcher so beautifully put it, the polar field precursor phenomenon in itself shows no unique relation to the dynamo type, and therefore cannot be used to conclusively constrain the dynamo type. Put simply, just because a surface field successfully predicts the next cycle doesn't mean the sun operates on one specific type of dynamo. This brilliant new math shatters that old assumption entirely. Predictability is a feature of multiple dynamo types provided the math linking the surface to the interior holds up.
By replacing purely statistical guessing with this robust physics-based boundary integration, we can finally mathematically prove which models actually work. So, with these incredible new mathematical tools unifying our understanding of solar dynamos, you have to wonder, how precise will our space weather forecasts become before the next cycle hits? We are literally closer than ever to truly reading the mind of our star. Thanks for diving into the explainer with us today.